And I think Dr. Zheng is not a new face for our PhD school, and she actually was a PhD student in our PhD school in 2022, but now she has become a lecturer in Griffith University, and what a fast transition. And she is a rising star in her area, and now she is currently a lecturer in the School of Information and Communication Technology at Griffith University. She completed her PhD degree in the School of Information Technology at Monash University. And her research focuses on data-centric machine learning and automated graph and machine operations with a particular emphasis on graph neural networks. And her work has been featured in prestigious journals and conferences such as IGSAV, PR, Neural IPS, ICLEAR, ICDM, and WW. And she was also a recipient of the 2024 Postgraduate Publication Award from Monash University. Now let's give us our warm welcome to Dr. Zheng. Next, I will hand over the microphone to her, and she will take us navigate through her tutorial about graph machine learning.
Thank you for Zheng's introduce, and good afternoon, everyone. My name is Zheng, and it's a great honor to be here today as a speaker for this PhD school, and thanks for Dr. Rocky's invitation. And actually, this event does hold a very special. This not work? This one not work? Okay.
I think so.
Okay. So this event does hold a very special meaning for me because I participated in this PhD school go back to 2022, and I remember that I even won a poster presentation award then, and I do get a lot of inspiration from this experience. And I do remember the Professor Felix talk about the data profiling, and then I do a lot of research about the data-centric AI, so thank you very much. And today I'm excited to share my insights with you all and give back to this community. So I hope my tutorial today would provide you more valuable perspectives. So today I'm going to talk about the automated graph machine learning operations workflow from a data-centric perspective. So here is a brief overview of today's contents. I will first introduce some background about the automated graph envelopes in data-centric AI. And then I will talk about two aspects from the graph data-centric perspective involving the data exploitation as well as the model development. And at last, I will talk about the future opportunities and the challenges faced for the automated graph envelopes. So first, let's start with what is automated graph machine learning envelopes in data-centric AI. So essentially, an AI system can be broken into two main components, the code and the data. The code usually means that the models, the algorithms, and which determine how this data can be processed, analyzed, and modeled. And equally important, the data itself can be taken as the fuel that powers these models. So data allows the model to learn, adapt, and make the reasoning and the predictions. So if we have poor quality data, however, it can lead to like the garbage in, garbage out problem for the model. So actually, we have been working on developing the models for decades. However, after so many years machine learning model development, this community has paid so much attention to select and design the right appropriate models for the specific applications. So in this process, there are a lot of vital steps, like first, how we understand the data that need to be modeled. And second, how we prepare the data as the model input. And at last, how we evaluate this model to make sure that the deploying this model could really benefit the real-world scenarios. So there recently has been a lot of discussions in terms of data-centric AI, which is taken as a discipline of systematically engineering the data used to build an AI system. So as a general comparison, different from model-centric AI, which mainly focus on the pipeline of model design, training, evaluation, development, as well as the deployment, which means the whole life of a machine learning models. In contrast, the data-centric AI focus on the comprehensive life cycle of data, comprising the various stages of data engineering, exploitation, maintenance, collection, and the exploration. So in the overall process of the data-centric AI, sometimes the models may not undergo further update or design or refinement until the data itself, the corresponding part could be considerably ready. Therefore, the data-centric AI, in this case, plays an important role in dealing with the highly messy and noisy practical data in large quantities. And taking the recent fast-developed large language models as an example, when the LLM model becomes more mature, more smarter, even the similar model architecture in different versions from the GPT-1 to current like ChatGPT 4.0, the amount of data used for training the models has been increasing. And the quality of data is also required to be improved. Therefore, we can see that the GPT models have evolved. There is being a consistent push towards using the larger data sets and ensuring the quality of data improves. So this basically highlights the core idea of the data-centric AI is to engineer the data to enable the great availability and the quality for together the model-centric AI for powerful model design. So here is a very simple example about why the data-centric AI matters. This is a question about inspecting the steel sheets for the defects. And here we can see from this image samples, there are some defects on the steel sheets. And we test different methods about the baseline, the model-centric methods, that means design different models, as well as the data-centric methods to clean this image data, so that we test different surfaces like the steel and the solar panel, the surface inspection, and all these results show that the data-centric method could improve more than the model-centric methods. So in this case, we would like to talk about a typical and vital installation in data-centric AI, that is graph data, which contains the nodes to present the real-world entities, like the research papers in citation network. And these entities are also connected by the edges to indicate that these papers' connections of cited and being cited. So therefore, the graph data has the ability to present the complex structural relationships in the real world. And actually, graphs data exists widely in the real world applications. For instance, we have social networks, and node presents the different people, and the edges indicate their relationships. And we also have the protein interaction networks and the chemical constructed graph for AI assisted drug discovery and the protein design. So notably the AlphaFold 3, which leverage also this graph kind of representations recently contributed to the Nobel Prize in Chemistry. So the graph data has its own application fields. So for modeling various graph structure data with complex and diverse characteristics, the graph neural networks has attracted a lot of attention in past 10 years. It achieves promising results for various graph-related machine learning tasks. And here I show you the core idea of graph neural networks is all about the graph convolution operation. It involves the core process called message passing, where a node's representation is determined by its neighbors by aggregating the valuable information from them. And this figure 2 just shows one of mainstream researches about GM model design is about how to design the effective message passing mechanisms. So in this figure, we show a more general design pipeline for a certain GM model. Given the input graph, we would first specify the graph data type and the scale, and then we build the model using various different computational modules, gene layers, operators, connections, and then we optimize these design models with different loss functions. However, when we take a step back and look at a bigger picture, we realize that the model design is just one small component in an AI system or machine learning operation workflows. So this is going to be a problem when we put too much effort on the extensive developing GM models from the research perspective. So the only focusing on the GM model design would lead to different potential issues. Like first, at the data level, the important role of graph structured data is usually overlooked. Actually, we design a graph machine learning model. The core of it is the graph data itself. It should be the primary research objective. And second, at the model level, most existing GM models are designed by our human experts manually, and we cannot guarantee these models would well adapt to specific graph data and tasks even for the real-world unseen scenarios. So the third part is about the deployment. The well-designed GM models and the well-trained GM models in our laboratory would be used for inferring on real-world test graph data, which usually do not have any labels, and we cannot see its distribution in our training process. So in this case, it could be very difficult to evaluate whether these deployed and well-trained GM models can be really good for learning the real-world scenario. So in this figure, I also show you an example about the graph out of distribution detection problem to show why the data-centric graph machine learning matters. And this problem, the graph OOD, is basically found out the out of distribution nodes or graphs from the graph data side. And from the table in the right, we can find that compared to different model-centric graph machine learning methods, even different learning paradigm, and the data-centric graph machine learning methods could lead more performance improvement, and that it does achieve better performance. Therefore, what we need is systematically consider the entire pipeline of building the production-ready GM models from the industrial perspective and for the real-world application scenarios. So at the beginning of the graph data input, we could consider the fully exploration about the graph data-centric engineering. And for the model design part, we could consider to automatically design GM model, which could be driven by different graph data with certain diverse characteristics. And for the deployment part, our final goal is to create the production-ready GNs for practical service. Therefore, we aim to develop such an automated, systematic, and optionalized graph machine learning workflow with GNNs, that is, automated graph envelopes. And we mainly focus on 3 stages, covering the graph data engineering, automated GM model design, as well as the GM model deployment. So specifically for the graph data engineering, we focus on 2 aspects. The first is graph data skills, and the second is about various graph data types. So we would like to know that the diverse and complex graph data types and its large quantities, how these factors affect our model design process. And for the automated model design part, we consider to use the graph neural architecture search technique to automatically develop the data-driven, even the task-driven GNNs. And for the GN model deployment, we aim to fully understand how we well-designed and well-developed GN models would perform when they make the practical inference on the real world. So from a very data-centric focus for all these 3 stages, today we will consider the graph data types and the skills, the data-driven graph NASP method, and as well as talk about focus on evaluating our developed GM models' performance on the real-world unseen and unlabeled test graphs. So if you are interested in more details about data-centric graph machine learning, and you're very welcome to know more about our survey work. And here we provide a comprehensive roadmap about data-centric graph machine learning, aims to process, analyze, and understand the graph data in the entire life cycle. And we focus on different perspectives like how the data would be improved for its quality and availability. And we also introduce some learning paradigm like how to develop the effective GM models. And we are expecting that this data-centric and model-centric AI could work collaboratively and under this graph machine learning operation workflow. So next we will have a detailed discussion about the graph data-centric exploitation, and we will cover the graph data skill issue and the diverse and complex graph data type issue. So actually in the real-world application, usually the graph data scale can be very, very large. As we can see for the citation network, there can be thousands and hundreds of papers connected, and actually modeling such large-scale graph would affect the GNN's deployment with very heavy cost. And here we list the model serving space of different graph data sets in terms of the model size, the training graph size, and the training graph's feature size. And it can be observed that actually the GM model size is not that big. and it can be very small, but the main part, the main cost lies in the training graph size and the graph feature size. This cost can be very huge. Therefore, if we would like to train an optimal GN model on this large-scale graph, it would require the repeat training and fine-tuning for the optimal. Like at the very beginning, we designed a model, we have no idea whether it's good or not, and we training this model on our data, and we find there might be some problem. We would like to adjust the model's architecture, the layers, the parameters, and then again we do this. So this would incur very heavy costs on even the data storage, this massive computation and memory. So in this case, there is a very promising solution called graph condensation. It aims to address the challenge of such large-scale graph issue. It aims to synthesize a compact, a condensed, a small-scaled graph, but it also requires this small graph trained model to retain the comparable test performance when they train the same GN models. And we can see in this figure, after applying the graph condensation technique, the number of the training models has been reduced to like 1,000. And the model's performance on the original test set, like the test accuracy on 4 different GN models, actually it did not hurt too much. So in this case, the graph condensation can not only reduce the above costs by supporting the GN training in a small scale graph and alleviate such graph data storage, computation, and memory costs. Actually, it can also benefit a lot of practical applications, even for our research, like the graph neural architecture search, the privacy protection, like if sometimes you do not want to share your privacy data to like other company or something, you can give him a substance, like give him a replacement of your original data. So specifically for the graph NAS, instead of searching a large scale graph with heavy cost, we could alternatively searching on a small scaled condensed graph data to accelerate like the GN model deployment process. So for graph structure data, actually, if we want to do the synthesized work, it has 2 components. We have to do it both, like the node attributes and the graph structures. And as we can see in this figure, the existing condensation works would condense the original graph to a smaller one with both nodes and structures. Actually, if we condense them both, jointly optimizing the graph structures and the node attribute would be a very complex learning objective. So we are wondering that could we just directly condense the graph structure data into the node attributes? So in our work, we propose a structure-free paradigm which uses an identity matrix as a condensed structure, so that we could only synthesize a small-scaled node site to present the original large-scale graph. And we can use this small-scale even node set to train a GNN. And actually, in this case, it can be equal to train an MLP, but it could also achieve the good inference ability on the original large-scale test graph. And different from existing works use like gradient matching schema, which is a specific technique. We use the long-term parameter matching schema, which implicitly encoding the topology structure into the node attributes. And in the meantime, we could enabling a long-term the gene learning behavior imitation. So here is the overall framework of our proposed structure-free graph condensation method. And given the original large-scale graph T as input, we first train a set of expert genes on the large-scale graph as a kind of knowledge base of the gene learning's behavior, and then we conduct the long-term training trajectory matching to align the learning behavior of the original large test graph and the small-scale condensed graph, or even the node set S, so that we could encode the topology structure into the node features. So until now, in each step, we could obtain a condensed data S. However, the problem is you cannot change the model and in the meantime change the data. You will never get the optimal solution. So how to make sure you currently the changing condensed graph data being the optimal? And we cannot directly or straightforwardly evaluate the data set without involving the training process of GNN. So here, we also introduce a graph neural feature score, like the 5 parts, and we use it as a kind of metric or measurement to define whether this current condensed graph-free data is optimal or not. This is a very dynamically process, and it can help us to find the optimal small-scale data as well as the optimal GNN model. And we conduct the node classification task by training this original large-scale graph and our condensed graph-free data with different condensation ratios. And our method achieves the best performance on 13 or 15 cases. Like for 5 data sets, and for each of them, we consider the 3 condensation ratio. And it could show that the high quality and the expressiveness of our condensed, even the condensed node site, this synthesized data for our SFGC method. So next, we will discuss the potential problem of diverse graph data types. Actually, in many real-world scenarios, the most common graphs can be the homophilic graph, where most existing GNN models are designed for homophilic graphs based on the neighbor aggregation and the message passing schema we talked about before. However, there is another graph type named heterophily, which is a totally different type with distinct properties with homophily. When the homophilic graph has nodes with similar features and even with the same class labels linked together. For example, in citation networks, actually a paper or a research work would usually set the reference paper from the same research domain. But for the heterophilic graph, the linked nodes usually have dissimilar features and with different class labels. For instance, in the online transaction network, the fraudsters might more likely to build the connections with customers rather than other fraudsters. So as we said, the core idea of current GNN models is about the message passing over neighbors along the graph structures. So it does fit the homophilic property for the same class neighbors. But when this applied to the heterophilic graph, it would not be good when the neighbors are in different classes and aggregating their information would not benefit this central node representation learning. Therefore, our focus is that possible to automatically design the heterophyly-friendly GNNs. And this model development process can also be driven by specific characteristics, even for different heterophilic graphs. Here we would like to introduce the graph neural architecture search technique and compare it to human-designed models, which are usually manually developed and non-automated. The graph-NAS method would significantly relieve the human efforts and automatically design the powerful GNN models driven by specific data and tasks. So in the right figure, I list two different graph-NAS architecture search methods, and there are basically two core components for the graph-NAS method. One is about the search space, like how we decide the final network architecture. Like at the beginning, we need a pool. And the second one is about the search strategy, like how we find the optimal architecture from the pool. So despite there are like expressive automation brought by graph-NAS, the mainstream graph-NAS methods still have their own limitations. The first, at the data level, there are many designs for simple relational graph structure data with homophily assumption. However, like we said, the heterophily property cannot be well modeled for the current methods. And second, from the NAS algorithm level, the existing methods usually design the coarse-grained GNN search space. Like in their pool, they have just very simple architectures come from existing GNN models components. So that means they cannot properly search in the right and comprehensive this space, so that they cannot develop the optimal GNN architecture. So here we would like to bring you our work that is AutoHack, which would be a good choice to automatically construct the heterophily aware GNN models. So what our AutoHack can do, first, it could automatically customize different and creative GNN architectures, specifically for heterophilic graphs. And second, it could contain comprehensive GNN architecture components, which can be very friendly to heterophily property in this heterophilic search space. And third, on this heterophilic graph, the AutoHack could effectively and efficiently to derive a GNN models with this heterophilic search space. So let's have an in-depth look at this heterophilic search space and search strategy in our method. Specifically, this search space have both macro-level and macro-level design involving various homophilic and heterophilic candidate operations for composing this search space, this AutoHack supernight pool. And then, given this supernight, the AutoHack could conduct the search strategy on it with a progressive training strategy, along with a heterophily guided like leave one out selection method to select the optimal architecture. So finally, the proposed AutoHack method could automatically tailor a GNN model driven by specific heterophilic graph. And here are our automated designs GNN, and we have 4 data sets. You can see that for different data sets, the data itself matches different model architectures appropriately. And we evaluate the proposed methods on also node classification task with heterophilic graphs. And we also test the highly heterophilic and the low heterophilic graphs for these automated GNs. So basically, with our heterophilic search space, it can adapt well for both high heterophilic data and the low heterophilic graphs. Okay, in the following, let's discuss, even we have this prepared data types, data skills, and these well-designed automated models which consider the graph data characteristics. What practical problem we can encounter in the real-world model deployment? So if we want to build a systematic graph machine learning workflow, understanding and evaluating a GM model's performance can be a very important step, even the beginning step for the GM model deployment and online serving. For instance, in the financial transaction network, if I am the GM model designers, I'm expecting that the developed GM models can be excellent, even in practical unseen data. For the newly emerging suspicious transactions, I could detect that. But from the user side, they would like to ensure that how they could trust your GM models and to know whether you could really detect the real suspicious transactions in their own data. So let's consider the conventional GM model evaluation process, which we usually do. It's a standard process in our lab. So we first use a training graph to train a GM model, and in the test or inference stage, given a test graph, we use a well-trained model to provide the predictions and compare them with the ground truth labels for calculating the performance metric. So that means in our standard evaluation process, we have some priori conditions that means at least we know the ground truth so that we can calculate the ACC. However, in the real world, the test graphs are typically unseen and lacking annotations. That means in practical GM model evaluation, first, we cannot access the ground truth labels of the test graph. And this also means we cannot directly compute the accuracy, this performance metric. Besides, we also have no idea whether this kind of there are potential distribution shifts from the real world, our unseen test graph between it and the training graph. We have no idea. So in this case, we have a natural question is, in the absence of the labels of the unseen test graph, can we really estimate the performance of this well-trained GM model? So we identify the answer of this question as a new research problem called the GM model evaluation. So given an unseen test graph without labels and a well-trained GM models, we are expecting that there could be an evaluator to directly output the performance of the current model, like the accuracy. This could be very practically useful where in the real-world cases such an evaluator may help us to do the model selection part according to our estimation. So assuming we have a model pool has well-trained and you want to know which model would perform best on your own data, then this is the time you use our GM evaluator. Here we provide a formula definition about GM model evaluation. So given the observed training graph, the well-trained GM models, as well as unlabeled and unseen test graph, the goal of GM model would be to learn an accuracy estimation model. It can be taken as a node classification estimator or accuracy rewriter. So To solve this problem, we propose a two-stage GM model evaluation framework with a product of GM evaluator. So this is the overall pipeline involving two stages. The first is the discrepancy graph set construction. In this part, we would like to understand comprehensively covering such training and test this distribution discrepancies into a graph called the discrete graph. And more specifically, we first extract a seed graph from the original training graph, and then we impose some argumentations to expand the seed graph set for creating a meta graph set, so that this meta graph set could have diverse graph data with diverse characteristics. We would like this meta graph set to cover more and more unseen distributions here. And given such a set of constructed meta graph, along with the training graph, we send them both at the well-trained GM model's inputs. And we could obtain this kind of node feature discrepancies by the D function. And also we can obtain the accuracy from the well-trained GM model's output. And we also preserve the metagraph's structure, its structure information. So using all these components, we compose the discrepancy graph. And then the second stage, we use the constructed discrepancy graph to train a very simple GCN evaluator. And this evaluator could directly output the estimated ACC. We also conducted experiments on 3 real-world graph datasets, and we're considering different potential training and test domain shift scenarios. And for each case, we evaluate 5 models. And basically, these experimental results are reported as a MSE between our estimated accuracy and the ground truth accuracy. And we can see that all these results could demonstrate there is not too much gap between our estimation and the ground truth. It shows that we do have this GM evaluator has the ability to estimate on the unseen and unlabeled test graph, even with distribution shift. Okay, so next we will discuss the future opportunities about such a automated graph machine learning labs in data-centric AI. So given such 3 stages, first, at the graph data level, we believe there should be more in-depth exploration, understanding, and management for the various graph data types, the characteristics. And for the GM model level, we are expecting more automation, explainability, robustness, fairness in the overall model development process. And combining the data and model levels, we believe the future models need better generalization and transfer learning abilities. So finally, for the application level, there should be more industrial views. We would like to know that how these developed models can be used. This could involve the continuous evaluation and the integration, deployment. Even sometimes we need to real-time monitor our model's performance. So in the following, I bring you some examples for each aspect. So first, for the data level, we might involve some dynamic graphs with more complex characteristics, and it does evolve with time. So we can see that when the time gaps goes larger, the model's performance dropped a lot. So that can be a very promising scenarios we could work. So second, the fine-grained automated design of GM models. So even we have already have a fine-grained or designed GM search space or architecture pool, sometimes considering diverse and complex data types characteristics, we might sometimes need more fine-grained design. And here is our work, of course, for different graph types. This is for multi-relational graphs, and we do involve more fine-grained GM model architecture supernet for this search space. And for the third part, I think we should focus on more graph data distribution shift issue and the corresponding graph learning methods. And that could covering different graph domain adaptation learning, like how we continue learning this model to avoid the forget old data, and also the out of distribution learning to find maybe some outliers in our data. So last, we enabling the continuous and online evaluation. Even sometimes our GM evaluator, we can see the training data so that we can calculate how our unseen tested data could be their discrepancies between them, but sometimes we have no information or access of how this model can be trained and the training data. So in this case, how can we evaluate the well-trained GM models for this online scenario? Okay, thanks. That's all for today.